Good morning, everyone. So let's continue our wild run through the machine learning. And our plan for today is speak a little bit about what is called unparametric methods, or the methods which come in without parameters, and you'll see what it is just now. And because that's, I think, that's what we're going to start with. And one of the things which we are going to talk will be those trees, which we've seen yesterday a little bit kind of in a blind regime, in the sense like we just use it without understanding what we are doing in the tutorial. So I will give you a little idea. So what are the trees and how the trees form a forest, and what kind of things one need to do to form a random forest, but very superficial. But I think it's useful to understand, at least to have the basic idea of how the things are coming together. Okay, and afterwards we are going to go to the unsupervised learning a little bit. So I will speak about methods to reducing dimension, essentially only about the PCA, just also because we don't have that much time. And afterwards, the rest of the day will be spent in explanation to you of certain things about neural networks, but also we will limit ourselves to the kind of generic so-called fully connected neural network. And afterwards, I will speak a little bit about, how the convolutional neural networks are built. Again, rather superficial, but generically. And if we'll have time in the tutorial, there will be the two last tutorials will be on application of these so-called dense neural network and convolutional neural networks towards the standard MES classification, which is very standard and typical example, but I think it's useful to have to see it at least implemented once. Okay, so, and for now, we're going to start with what is called nearest neighbors and decision trees. And again, so sorry, let me say it again. My slides, and I will be very carefully quote, my slides are based on the slides from the applied machine learning course from the Penn University. Okay, so kind of these methods are one can call it a different kind of learning, because when we are talking about linear regression, or when we are talking about also logistic regression, or kind of the classification which is based on those sigmoid function and exponential with a linear function, essentially we have a parameters in the model, and in order to train, and we have kind of a process of the training the model. So, and in these types of models which we are going to talk now, there is no kind of like a training per se approach. So we can, it's kind of, it's all together, and you'll see what it is on the very simple examples. So first, K nearest neighbors. So let's consider so that we have a binary classification, yeah? And we have the following data. And the data is the size of the t-shirt for the customer or whoever, yes? And we have a height of the person and the weight of the person. And if we plot the height of the person and the weight of the person, and whether the person needs a large t-shirt or medium t-shirt or large or not, so we're going to, the red dots are no, the blue dots are yes. And the question is, then the obvious question is, okay, so if we add, yes, kind of we have an input with the two features, height and weight. We have some entries, and in this example, if there was a CSV file, I think here was 18, yes, and we have a yes or no answers, yeah. So, okay, so now we get a new input, and the question is what it should be. Did this person who have a height of 161.5 probably, and the weight of 63 kilos or 62.5 kilos, that person, if we assume that it's coming from the same distribution, would require a large or small t-shirt. And kind of we could try to answer this question using this idea of the nearest neighbors in a couple of ways. So we can, I mean, of course, apply some methods which we done there yesterday, but what we can also do, we can just check how many kind of, what are the closest points, what are the closest nearest points to this new point, new input. So we want to predict category of the label of the new point, finding K nearest neighbors according to some distance metric. And you see already we already see that although there is, it's called non-parametric, but we already could see the parameters. Yes, first of all, the number of neighbors which you need to take into account, and distance. As we're going to see, you can measure distance in the different ways. And as a function of the how we measure in distance, we're going to get, or we might get, a slightly different results. Okay. So what we need to do to predict a new value within these k nearest neighbors, we need to find the k nearest neighbors and average the values which are associated to the neighbors. Okay. So, for example, in this case, if we take a 3 nearest neighbors, according to this is clearly something like a Euclidean distance, yes, so kind of a standard, Pythagorean or Euclidean distance, so square root of sums of the squares. So we're getting the answer that the person is requiring large t-shirt, but if we take 5 nearest neighbors, obviously kind of the majority of the points which are getting in this circle will be the answer will be no. So it should be a person with a medium t-shirt. And that's create to you an obvious question, like, if you have a real research question, kind of like how you can optimize this number of neighbors which you need to take into account in order to predict, in order to do a nice prediction. Okay. So, and also what does the nearest means? So in order to define nearest, we need also to define a distance. And as I told you that we have standard Euclidean distance, but there is also what is called L1 distance, which is just sum of the differences of the absolute values, and what is called infinity distance, which is just the difference between the kind of the absolute value of the difference between the maximum over the distance between the sum of the two components. So you essentially need to take the difference between the all components, and the distance is equal to the maximum out of them. So this is called infinity norm or infinity norm-based distance. Okay. So, and as the function of that, if we're just going to draw what is called the decision boundary, or kind of the boundary which is deciding in which class you are as a function where you are, we can get a slightly different answers. Yeah. So kind of like for the L1 distance, and for the kind of, we can get a boundary like this. For the L2 distance, boundary like that, and for the L infinity distance, is boundary like this. And you see, in principle, they look pretty similar. Yeah. So we have the boundary is kind of a line, more or less, which is separating the orange from the blue, but the particular shape, and if you are somewhere close to the boundary, that you could be easily misclassified here and there. Okay. And what if we need to measure distance not between the numerical values? That's another problem. And there are kind of the serious applications of that. For example, this Hamming distance is very often used, is Hamming distance. So kind of if we need to measure the distance between the two strings. So, and the Hamming distance is the number of characters that are different in the two strings. And this distance, in fact, is very often used in genetics. So when you need to kind of construct trees or hierarchical trees, which describe kind of your kind of the genetic trees, you use the Hamming distance to decide, how to jump between the branches of the trees. There is also something which is called edit distance, which is, how many characters you need to insert, replace, delete to go from one to another. There is the distance between the sets. So, and the distance between the sets is just the number of elements in the intersection of the sets, so number of same elements in the both sets A, B, and the number of in the union of the sets A, B, the ratio, kind of this ratio of these two numbers. Yes. And kind of like the distance between the sets, between the n-grams and characters substrings of the strings with n-1 character padding. Okay, so kind of you can do kind of string like this and string like this. So you can calculate what is the distance between the intersection, or kind of what is the intersection set, that would be this three elements, and what is the kind of union of these guys, and that would be all of that. And the distance will be 3/9, 1/3. So you can measure the distance in the different ways, and that is fine. Just be aware of that. And if suddenly you need to do something like k nearest neighbors, but not for the numerical data, know that, okay, so the fact that you cannot apply your favorite Euclidean distance, this distance, yes, kind of square root of the modulus squared. It's not a problem because this could be done. Okay. So, but what is the what are the problems of the k nearest neighbors? K nearest neighbors are very strongly depends on the scale. Yeah, because if we just see this is one and the same data set, but where this axis x1, you see here is plotted from -2 and 2 so that you can see it nicely, or you just rescale it. It's a little bit squashed, but in this case, it's just it's just a wider scale. But obviously, the way how you're going to measure neighbors will depends, because again, the distance depends on the definition of the distance depends on the scale. Okay, and there is even more thing which people less aware of when it's relate to the calculating of the distances or calculating of the volumes. It's be more precise that in general, it's one of these manifestation of this generic statement of the curse of dimensionality. So when you have so when we need to have when we're dealing with very multidimensional data, what's happening is that a lot of our intuition, which we get used about, about the two-dimensional flat things or volume things, do not work. For example, if we consider a sphere, yes, in d dimension of radius r, and we're going to calculate how much of that sphere is lying beyond 0.99 r. So how much is the volume of this little shell or little sliver, which is from 0.99 r to r, compared to all the rest. And for our casual three-dimensional intuition is telling us it's nothing, and it's really mathematically nothing. It's 3%. But if you are in 100 dimensions, it's already 63%. And if you are in 1,000 dimensions, it's already 99%. So essentially, what does it it's telling you, so that as you increase the number of features and you need to calculate more and more, go through the more and more dimensions, suddenly a lot of things which we have which we get used to in our normal three-dimensional world, so to say, breaking down, and we need to keep into account. And from this point of view, it just using distances might be unreliable predictor from our perspective, or from our intuition point of view. Okay, but what parameters are we learning? And if we think broadly about parameters is everything which is required to produce an output for a given model. So model class plus parameters plus new input give us predicted value. So for KNN classifier, for this model class, the parameters essentially is a full data set. And if we use method like this, the parameters, or it's either all training data, it grows automatically with the training data, and it's called non-parametric because there is no extra parameters. But in fact, in order to do something, we need to use it with a full data set. But these methods are quite useful, very simple, works very well. And but the main thing which one need to try to find out, and the main problem, you can play with the distances, you need to find what is appropriate number of neighbors. Yes, you play with the distances, you play with the k, and you find what works, and it's tend to work well in practice, but yes, scalability is an issue. Okay, so that is k nearest neighbors. But again, it's a very simple algorithm. It was one of the first algorithms which was also very easily generalized, for example, in the quantum machine learning domain, because it's relatively straightforward. And the distances is something which is relatively easy to measure also within the quantum mechanical domain. Okay, now let's go for the trees. So another non-parametric way. So what is the trees or decision trees? We intuitively know, because in the moment when you begin to think logically what you need to do, you are building your decision tree in your head. And here we have a very simple example of the decision trees which are used in medicine. And supposedly, it's taken from 2010. So this probably might be even still working decision tree, which medical doctors are using. So yes, if you need to treat a child with a fever, and if the child of the age is above 2 or below 2, you don't give him this special class of the medication. If above days with a fever is more than 2, and the age of the child is about 3 years old, yes, you can use that medication, which is some sort of antibiotics. And if below 3, you don't use. So, and this is well-defined structure, for every child which is coming with fever to the good doctor based on this diagram could decide what to do. And decision trees is is something exactly similar. So if we want to make an attempt to formalize it, we need to formulate on the level of the Boolean statements, statements yes or no, or true or false. So it's essentially the same thing. Yes, days without fever greater or equal than 2, true, false, and so on. Okay. So now if we wanted to do the same thing, but we wanted to do it for, some data set and an automatic regime. So what should we do? We should grow the tree. So we need to start with we have the input data. Yes, so we formulate some condition. For now, we don't know which, but we will see now which and how. And if it's true or false, we get the 2 branches, yes. And afterwards, we formulate next condition and check it on the subsets here and subset there. And we do it until we build the tree completely, or whether it's good to build the tree completely or not, we'll see, so to say, just now. But the idea is we're just building the in the same way as in here. So we need to derive an approach how we can do it in automatic regime. And obviously it's done because we were using it yesterday. Yeah. So in a little bit more formal way. So if we have a data set of labeled instances, so we have our inputs and we have our answers. Yeah. So we can define a subset, we can choose how we're going to build, the branch. For example, we want to build the branch for the value of one of the index of one of the features equal to new. And what do? We build 2 leaves. Yes, they pick the best feature to define a partition. We're setting up a new node, which are divided by the value of this node, and we decided. But of course, there is a nice question. So how we decide which feature is the best? And the obvious answer, or not obvious answer, but the simplest answer is we just do it randomly. So there is nothing wrong in building it at random. So we take, arbitrary feature, we take an arbitrary value in the distribution of the feature, split the data set in 2 as the function of that feature, and continue and see how good we are doing. But of course, the question is, can we do better or not? And the reason why we're talking, of course, you can do better. And in order to do better, we might use some philosophical principle, which is coming from the monk from the 13th century, which is called Occam, and it's a very famous philosophical principle, which, every physicist which is study relativity should know, because that's what is used when Einstein supposedly was thinking about relativity, so that he was thinking about the Occam's razor, and that's why he eliminated the if here. And the basic idea is that, if you need to design an explanation, you should go you should go for the simplest answer. So in our case, there's simple, consistent explanation is the best, or the explanation which can give the better explanation of the cut, which will give us the better explanation of the separation. And what does it mean? And in order to understand what does it mean, let's look at the subset of the data set. So there is a data set of the people who have a diabetes, and it's have multiple columns, and but let's look at the 2 columns and just only on these lines in order to understand what's going on with this the application of the Occam's razor ideas. So we have one column is whether the person or whether the patient or person have a high blood pressure or not, and what is the education of that person. And this is the kind of the target column is whether the person is diabetic or not. And we have the kind of the blues are those who don't have a diabetes, the oranges, those who have a diabetes. So, and if we just cut it with a high blood pressure, yes, have a diabetes would be this group, no would be this group. And if in education, so we'll have a greater split. But the question is, which split is more informative? And I think here it's more or less, or at least one can argue kind of like what is more informative, but one would like to have it in automatic way or kind of in systematic way. So what do you think? Which split is more informative in this case? Why? So I get an answer, blood pressure. Why? No, but this you don't know. It's more likely to be statistically significant. Sounds good, but we have no clue about that. You know, kind of like because we have some background ideas, but you know, I want to see different answer. The feature zone, yes, the spread between the two groups is. I mean, I would say, you know, kind of like why I would say that the blood pressure is because it allows you to eliminate, you know, half of the cases immediately, you know, because, you know, after you say high blood pressure, no, everybody there doesn't have a diabetes. So that you can conclude, you know, if you, according to this subset, you know, we don't know, does it work for all, but the fact that, you know, the high blood pressure no corresponds to the no diabetes is already good enough, you know, cut and you can see kind of what other relevance in the high blood pressure category. But we need to, oh, you see, we have a different opinion. Very good. And we have a professionally biased opinion, I think, yes, because education, in case you, because of the stresses which are related to the educational level. But okay, I mean, that sounds very interesting. And, you know, I wouldn't comment on that because, you know, my opinion might be biased in this case because I'm also representing the education, kind of the people at the educational system. But you see, kind of the fact that we have various opinions means that, you know, it would be nice to have some criterion to characterize it. And I'm going to very roughly to mention to you which is that is criterion is, because, you know, it's good that we have an idea about what the education is and whether the education might be relevant or not for diabetics or for to having a diabetes, or is the high blood pressure relevant or not for diabetes? I don't know, but, you know, kind of like we have our sense and intuition and we can try to make sense, but, you know, machine don't, and machine needs a formula. And now what we want to have some sort of the formula which can characterize, you know, the subset from the point of something which can tell us. And let's consider kind of the example. So we have sets of the circles and the crosses, and if the number of circles and the crosses is the same, so we don't know anything. So we can call it, you know, maximally impure. So, and if we have only circles, it's minimally impure because, you know, it's well defined. So here, if we draw a random person or random object from the maximally impure with probability 1/2, we're going to get, you know, circle or cross. From the minimally impure with probability 100%, we're going to get circle, and also with probability 100%, we're not going to get cross. So we have and here we're coming to the word which, you know, I haven't been speaking yet too much about, which is called information. Yes, kind of an information, not in the sense of, you know, in a kind of the common sense, but in the sense of information theory in the computer science sense, because in the minimal impure case, we get the maximum information about what is inside of our system or kind of in our circle. In maximal impure, we have no information, or information is we don't have, and kind of in between we can characterize. And if we need to characterize the information, there is one measure, and that measure is that measures entropy. Yeah. So entropy was suggested in the content of information, was suggested then for Neumann and it's a very simple thing to, not so simple thing, but it's a well-defined thing to calculate. So if we have a y to be any discrete random variable, which can take n values, so we have y could be anything out of n values. So it could be 0, 1, 2, 3 for n minus 1. So the entropy of this and we have some distribution of y's, yes, and we have some probabilities that with the probability, if we have a box with the red and the blue balls, yes, and we have 5 red balls and the 2 blue balls, the question is what is the entropy of this system? So we need to calculate what is the probability to grab a blue ball, what is the probability to grab a red ball, and so on. So how the entropy is calculated? It's a probability that our random event get a value I on log of that probability. And in principle, the base of the log doesn't matter, but because the important thing is that's a log, but by whatever tradition in the information theory, it's a log 2. Okay, and we need to sum over all possible outcomes. Okay, so strictly entropy maps from probability distribution to an impurity score. Okay, so and why that working? So let's see for the very simple case of for the very simple case of the true events. So if we have, what would be the entropy according to this definition for the if we have only circles? So we have a circle with a probability 1. So if we take a random object from the minimum impurity class, what is the probability to have that that its circle is 1? So we get 1 log 1 minus 0 log 0. Yes, that's the probability of the cross. Yeah, and we get 0. And what is if we get the maximum impurity? So if we have 3 crosses and 3 circles, it's the probability to draw a random circle is 1/2. So we get 1/2 log 1/2, and cross 1/2 log 1/2. So we sum it up, we get 1. And that's where the fact that we're log 2 is useful, because in this case we're going to get 1. If we were the base exponent or log 10, we'll get something different, which is just up to the constant. And if we generally plot if we say that there is some random distribution with probability p to get a blue circle and with 1 minus p orange cross, and we plot it for all the p's from 0 and 1, we get such behavior of the probability. So when the entropy, so not the probability, but entropy. So the entropy, the low entropy would imply minimum purity or maximum order, and the high entropy implies maximum impurity or kind of minimum of information or maximum of disorder. Okay, so and how that can help us? That can help us in deciding which feature do we want now to cut. And in which way? So we can compare what was the entropy before we're doing the cut and after we're doing the cut for the given feature at the given cut. And in case we get kind of the biggest gain of information, when we do the cut, that cut we do. So it's a very simple logic. So you do every time you do the cut when you build the tree on the request that you should gain the maximum information. That's irrelevant of what it is. Is it a high blood pressure education or it's something else? Okay, so what we now need to do for this simple example, we want to calculate the information gain. So we have our entropy, and now we need to calculate this information gain for this case. And this way of writing, this HD x nu is equal, xj is equal to nu, sometimes it's called conditional entropy, which just means that it's an entropy where this value is fixed on the probability of that value. And we're summing up for all of them. And in this case, this information gain could be written as the difference of the entropy minus conditional entropy for this particular feature. Okay. So if it sounds a little bit exotic to you, and you think that, you're not too good with entropies, you can just think that, we do the cut in the tree. So when we're building the tree, we're building the branches based on the condition, and this is one of the conditions. There are different conditions, and there are different ways, but this is the simplest idea, so that we get the greatest information gain. So we get the greatest information quantity, we learn maximum new information by doing this split, so to say. Okay, so how we can do it on
Is it my network or did Prof. Ilya?
no, I think it's your net.
Oh, okay. You are
Okay.
back.
Okay, sorry. Can you hear now?
Yes, but we can't see the slides.
Maybe I need to share them. Maybe it's my thing. Okay, let me. Okay, let me reshare them. Maybe it was my network. I don't know. I don't mind it. Oops. Okay. Can you see the slides?
Yes.
And participants, have you lost me? Have you lost me on this slide or on the previous slide?
The next one. It was this one.
This one. Okay. So let me just reiterate. So okay, this one. Okay, good. So let's first calculate the information gain on this simple example. Yes, so we have 14 blues, 16 oranges. We cut it into these two subsets. Yes, 1 blue, 12 oranges, 13 blue, 4 oranges. Yeah. So we can calculate the entropy of the big blob. Yes. So we have 14 blues over the 30. That's a probability to get a random sample of the blue color, and the 16 over 30 of the orange color. Yeah. So we can calculate it, and that will be 0.996. Now we're calculating the entropy of each child. Yes, kind of like or each subset. So 13 over 17 of the blues and the 4 over 17 of the oranges. And the similar thing here for the 1 blue and 12 orange. Yes, 1 over 13, 12 over 13. So we get entropies. But now what we need to do, now we need to calculate on the probability kind of to get each of the corresponding subsets. Yeah. So, and that's why we need to calculate kind of this weighted mean. So 17 over 30. So the probability of this subset on the entropy of this subset plus probability of this subset, probability to get in this class or on this side, on this subset, we get this number. And so what we get, the information gain is difference between these two numbers. And essentially what we now need to do in order to build the decision tree, we need to go for the all features. So for the all entries of our x's and consider the splits. And when we consider the splits, we need to decide, kind of like calculate this quantity information gain and choose that one which gives us the biggest value. Okay, so, and that's why we only consider that's why we're only considering here 2 features, because otherwise we'll be here till Friday. Okay, so we can kind of rewrite all of our entries like this. Yes, kind of. And so we need to compute information gain for our data set when we're cutting by the high blood pressure or when we're cutting by education. And check. The version of PDF I have has missing info on this slide. Is it just me? I'm not sure because I use absolutely the same slides. I'm not sure how that's possible because that's the same PDF which I uploaded. Okay, so, but first let's start with the entropy. So the entropy of the total data set. So we need to calculate how many people with the diabetes and what is the probability if we draw a random person from this set will have a diabetes or not. The slides are in the canvas. Just go to the canvas, week 2, Tuesday, info 2ML, day 2. Yes, that means that the parent have more information. Of course. I mean, it's kind of, okay, more information is got, its entropy is higher because now you're splitting and by splitting, you're creating some sort of order, even by random splitting. Slide 31 have missing info. I don't know what is the slide 31 is. And why it had the missing info, I also don't understand because it's identically the same slides. Okay, so let's calculate the entropy for the full data set. So we have 12 entries, yes, 4 diabetics, 8 non-diabetics. So if we draw a random person with a 4 out of 12 probability, we're going to have a person with diabetic, and the 8 out of 12 are non-diabetic. Yeah, so we can calculate the entropy of the set of our subset before we do the split. Now, now we're doing the split, and the split is into the high blood pressure. So high blood pressure, yes, we have this group. Yeah, so in what we have here, we have 6 items here, 6 items here. So in our weighted averages, kind of the probability to get it into here and here by random is the 6 out of 12. But now what we calculate, now we calculate the entropy of this subset. And here we have 6 entries, 4 diabetics, 2 non-diabetics. So we get 2/3 log 2/6, or 2/6 logs 2/6 plus 4/6 log 4/6. And here it will be 0 because it will be 0 log 0 plus 1 log 1. Yeah. So we can calculate. So the conditional entropy for the cut high blood pressure is equal to this. With education, it's a little bit more involved. Yeah. Because we have 1, 2, 3, 4, 5 different groups. We need to calculate what is the probability to get into each group. So in this group, so we get in total 12 entries. So here is 1 of 12. So by random, we get here in 1 out of 12 times. Here, 1 out of 12 times. Here, 3 out of 12 times, 3 out of 12 times, and 4 out of 12 times. Yeah. And we need to calculate the entropy is now of each of these subsets. So where we have only 2 ones of blue, over there entropy is 0. Yes, because it's again, it's a kind of well-defined entropy. So no, we get non-zero entries only when we have some mixtures. So where we have the three patients, we have kind of 2 inverse cases, 1 out of 3 log 1 out of 3, 2 out of 3 log 2 out of 3, in both cases, but in reverse order. And in the last case, we get 3 out of 4 log 3 out of 4, 1/4 log 1/4. interesting. Really interesting. Okay, I don't know what to say because I believe you, but what are you using? Are you using, I mean, it looks like Adobe. I don't know why. Sorry, I really don't know why. Because, yeah, it's the same slides. I can try to check.
Prof, I've checked and I see the same slides that you showed. So maybe they can just refresh and re-download the file.
Yeah, maybe because, you know, even in the preview, I see the full information. I don't know why. I mean, that's a little bit out of my control. I'm sorry for that. Okay, so let's go back to the calculation of the information gain. So when you see kind of like by doing this calculation, we can calculate the information gain, or we can calculate the conditional entropy, and now we can calculate the differences. Yes, because the entropy of the original data set we have, and now we have two conditional entropies. So, and what we get? So we get that information gain in the high blood pressure case is larger. So it's logical first to apply this cut, and maybe on the next stage, we can do an education. But this is, okay, so this is the basic idea how you build the trees. But also the next question is whether we need to do a next cut or not, because what we need to also remember that, you know, if we do too many cuts, or if we describe test set too well, we can get into the overfitting scenario, yes? And the question is, can we avoid overfitting in some way? So of course we need more training data, we need to remove irrelevant attributes, we need to stop growing. So kind of like, we don't build the trees until, you know, we're done. No, we need to stop growing when the splits are not getting too much of the statistically significant information, which means that, you know, we can say that, okay, if we get an information gain from any split smaller than certain quantity, which, I don't know, 0.05, I don't know, in that case, we're not splitting at all, so we stop. Or what we also can do, we can grow full tree and afterwards cut the lower branches. Okay, so, and of course we can play all the standard game with the cross validation and some other tricks. Okay, so the stop growth is one of the ways which is naturally implemented in a scikit-learn, and in scikit-learn we can set the maximum depth, and the maximum depth parameter in scikit-learn in the forest and in the trees is exactly, you know, how deep you're going, how deep is your tree. So you can also set the minimum number of samples per node, which means that, you know, on how many samples do you want to do the calculations, and minimum number of samples per leaf. Okay, so we can use all the standard k-fold cross validation to build the tree, or we build the perfect tree and cut it off and cut the lower branches. But again, luckily for us, it's all implemented already in the scikit-learn or in any other approaches, kind of like, as we're going to see. I mean, there are other packages which are used to build trees for some, or build forests, to be more precise, or build some other ensemble ensemble algorithms, and they are, yes, kind of like, it's all implemented, but you need to understand what are you optimizing when you're optimizing the parameters of these kind of models. And there is one more idea how to want to avoid overfitting. And that idea is related to the idea of the forest. And it goes like this. If we build a single tree, we can very easily overfit. But let's do the following. So let's do the multiple trees, and let's make sure that the trees are not very large. So we can kind of cut them, or we can even do more. We can train the trees, each little subtree, so to say, on the subset of our data. And afterwards, what we do? Afterwards, we just apply voting on the data. So we just average the results. So afterwards, we applied and we average the result. And in fact, this idea is called the ensemble approach, and it's extremely powerful. And it's not only powerful in practice, there is also certain mathematical guarantees for that. And so how you build a random forest. So now you know, kind of now we're coming to the explanation what we were using yesterday. Yeah. So kind of what is a tree? So tree is this kind of object which is built by calculating information gained in the data set. So you can do it sequentially. But what you can, when we're asking for random forest, what we're doing, so we were doing the following thing. So we're taking, or algorithm were doing the following thing. It was taking all the data, it was making a subset of the data, of input data, training the little tree, getting the classifier based on, or in that case, regressor on each little tree. And afterwards, when you apply to the total training data or to the test data, it's kind of using the training data, it's train the voting mechanisms, and it's create the final call for the answer based on the input kind of from the each tree in the forest. And kind of these kind of approaches are extremely powerful. There is a, so it's a statement that somebody could not hear anything, but it looks like that it might be the issues not on, I think everybody else could hear me. Yeah. Okay. So, and that's what we were using yesterday. Okay. So how we are training a decision tree in a random forest. So we draw a random data sample. So we grow a small tree. And afterwards, we repeat this procedure. So we build the K decision trees, and afterwards we just do a majority vote. And this is one of the ways how we can do it. And this, in fact, is subclass of this larger class of methods, which are called ensemble, which we are going now to discuss. One of the most popular classifiers for the big data. Yes, kind of like, and the reason is we're going to see just now. And the reason is, first of all, there is a mathematical reason. And the mathematical reason is that there is a, your poor classifier, which doesn't work too well, is called the weak classifier. And there is a mathematical theorem which is saying that if you have a large enough collection of the weak classifiers, you can construct using the voting and using some kind of assumptions about, essentially the idea is that your weak classifiers should be run on the different parts of the data set, on the different parts of the data. And if you take enough of them, you will be able to build a strong classifier, meaning that the classifier was or regressor with a very high accuracy. Okay, so why the random forests are so popular? They're scale invariant. They're much less susceptible to the overfitting than plain decision tree. And why? Because, it's really a bunch of undertrained classifiers, which doesn't have a chance to start overfitting. Yes, it can be generalized to the continuous data, and we've been using it for the regression yesterday. Yes, the training is highly parallelizable. Yeah, why it's highly parallelizable? Because we need to build a bunch of independent trees. So you can build the independent trees on the independent sub-data sets in parallel. So you can give it, to the parallel processors or to the parallel, parallel machines in the cluster. Okay, so, and this is one of the ways, this kind of the ensemble methods is really one of the strategies for increasing what is called the model capacity. Because so far, when I was telling you, how we can make our model to represent more and more data, what do we need to do? We need to pick a richer model family. You remember with the linear models, I was saying, we need to take a more and more involved features, or we need to do some feature engineering. But ensemble is a very good, easy idea, so that you can just average over the bunch of bad classifiers, or weak classifiers, and what you get a very good, you get a very good kind of structure. Okay, so, and the basic idea is that you learn the bunch of the base models, F1, blah, 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 Fk, and construct by some rules. And, as the function, how you construct a strong classifier, you get a different essentially types of type of these ensemble methods. And as a very simple example, or not simple example, Netflix a few years ago have a competition for the movie recommendations. So the goal is, yes, to predict how user will rate based on users' rating of other movies, other users' rating for these movies, and no other features. So, and it was a $1 million prize. And the idea was that to do 10% better than the Netflix recommendation system. And the people who won, they use an ensemble over 800 kind of the rating system. So it was kind of a smart averaging of the 800 of other classifiers. But this is just to give you an idea that, this is extremely powerful. This is extremely powerful methods, and they can be used on top essentially of any methods. And if you would try to follow, I don't know, any, kind of data science competitions, usually the solutions which are winning are really related to top-line ensemble methods. And, you can apply these ensemble methods, these guys could be any models, including neural networks. So, and that's what usually happens. People will build some neural networks, some other models, and afterwards they will use some specific strategies how to, in a smart way, to join, kind of to perform the voting between the results of these models. Okay, so what can you do? So how you can kind of join together the single classifier. So you can build something like a random forest, or you can do what is called gradient boosted decision trees. So essentially you can use a gradient descent type of algorithm, but in the reverse direction to increase the precision. And the basic idea is very simple. So what we've seen with the random trees or with random forest is just simple averaging. Yes, so we have the total classifier is just a simple average of the kind of weak classifiers. You can do it, for example, for the kind of here it's for regression. Yeah, so I'm sorry, I'm calling it classifier, but this is a regression. So if we need a classifier, which, for example, for the binary classification, so we just sum up the prediction of the k classifiers, and if it's above the k over 2, so it's a class 1, and if it's below k over 2, it's a class 0. Okay, so what else can we do? We can be a little bit smarter. So we can do a weighted average, and that's already the first way how you can, and you should really see it, as a recycling of the same idea. You can build a linear model based on these weak classifiers. So you can see the weak classifiers as the features. And now you train for betas. So you train these classifiers, and afterwards you train for betas. So because, different models could be better or worse. So you can have a bunch of classifiers which are okay in the one subset of the data, but diverse on the other subset of the data. And you can really might need to do some smart redistribution of these coefficients. Okay. So then generally, yes, you could have, in principle, any function which is given by the parameters, and you can use these weak classifiers as the input structure. Yes, kind of like, for example, you could have a specially trained functions which are trained on the performances of the classifiers, which might be some nonlinear function of the input data, and kind of you can think of that and the experts who knows which classifiers are working good or not. And this will be not just because the difference to the linear classifier, when this is just a coefficient, that this is also depends on the which part, or which is a typical entry of the data set, or which, if you just think for a second, if you're thinking about the trees, on which kind of typical leaves are you falling into. Okay, so and there are multiple other strategies, but just the very basic idea, what this idea of the random forest is doing. Okay, so successful ensembles, yes, requires diversity. So ideally you want to have a different model families, different training data, different features, different hyperparameters. And the intuition why the ensembles works is really that, that each submodels are making independent mistakes. Just think for a second of image like this. So let's say that we have, three models, yes, and they are not perfect, they do mistakes, but if they do mistakes on the different inputs, so if we just, take a majority vote here, yes, so we say that, oh, will be always correct, yes, using only these three models. And this is the basic idea of ensemble methods. And of course, to make sure that your data or your kind of sub-algorithms are making mistakes on the different input data is also an interesting and it could be a challenging task. That's why you need to have, diversity of models. Okay. So are we good here? Because now we're going to the unsupervised learning. Okay. So let's go and let's speak a little bit about the unsupervised learning, because it's also a very powerful and useful tool. So we were speaking about classification and regression. And now let's speak a little bit, very briefly, about the, if we just have an input data access, yes, without labels, and we need to find the structure in the data. And this could be, this could be as it is, like, that we are finding structure in the data, or this could be kind of a very useful tool, I don't know, before we do a supervised learning. Okay, so what is typically done using these unsupervised learning approaches? So the very typical case is what is called dimensionality reduction. So if we have our data to be a d-dimensional, so it's kind of like vectors with a d component, so we have a d features. So we want to map it into some function of these vectors such that, so when we want to find such a function, such that this is also a vector, but it's a vector in much smaller dimensional space. So, and if you can successfully do that without losing too much of information or too much relevant information, in that case, the model or kind of the data which is given in the lower dimensional space is much easier to analyze. The special case is clustering, and kind of when these functions are mapped to the numbers. Yes, so kind of we can have a clusters 1, 2, 3, and so on. So you could use these dimensionality reductions for feature learning. So you can learn what will be the good transformation of your data to give you good results. For example, it's used for the compression into the, for example, JPEG standards. And it's also could be used, for example, for the visualizations of your data sets to make a sense of your data sets. Okay. So one of the simplest and scalable techniques is the k-means clustering. So what is a k-means clustering? It's a very simple idea. So we have a data set. So we have input data, endpoints, and we want to discover a mapping. So we want to cluster them to the certain number of classes, k classes, and we need to specify how many classes that discover some natural grouping. Yeah. And we need to find what is a good function for that. Okay, so we could really see that, for example, if we have a dots here, it's very clear that, if we add yellow dot here, it should be in this cluster. If we add yellow dot here, it should be in this cluster. If we add yellow dot here, it should be in this cluster, but where should be this guy in? Should be in this cluster or in that cluster, how we assign the clusters. Okay. And in order to do that, we do it with that k-means algorithm is exactly answering to this question. So what we need to do for each cluster, we need to define a centroid. Centroid is a spot which is on average distance from all representatives of the cluster. And for any new sample, you assign a cluster whose centroid is closer. So if we calculate the distance from this guy, from this guy, and from this guy, from this guy, and from this guy, and averaged out, we are going to exactly end up here. So, and when we get a new entry, we calculate the distance to the centroid from here, and from here. And obviously, it looks like if it's Euclidean distance, this yellow guy will belongs to this class. And it will, of course, automatically will also move a little bit the centroid. Okay, so what and how we do it? So we start with some data distribution, and we, in principle, we assign randomly centroids, recalculate stuff, and find the centroid and adjust it iteratively. Okay, so let me do it a little bit more formally. So randomly choose K clusters because we don't know how many clusters, so one can start by randomly choosing them, some number K. And we need to do the cycle until convergence, assign each point to the cluster which is closest to centroid. So we randomly choose these points. So we assign all the rest points to the closest centroid. Now we re-estimate the centroids based on the points which are getting to the corresponding cluster. And do it again. So and we do it until the centroids. So until this guy will move here, this guy will probably, this guy, I mean, okay, this guy is already here, so this guy will move here, and this guy will stay there. Yeah. So kind of if we start, that's how it will go in. So everybody who is here is closer to the yellow guy. Everybody who is here is closer to the green guy, and so on. So, and as we loop through, this yellow guy might start moving in this direction. This guy might start moving in this direction. The green guy might start moving in this direction. And the blue guy is perfectly fine where he is. Yeah, and kind of you do it iteratively, and you definitely find some conversion. Yes, but of course, here again, we have a question of the distance. Yes, and here we're saying what the distance is, and the distance in this case is a Euclidean distance, but one can play with the different distances. Okay, and the problem is that this k-means is sensitive to initialization. So if we do some random initialization, we might end up in the different centroids. Sorry, I'm doing a lecture. Okay. Sorry. Okay. So where I was, sorry. K means is sensitive to the initialization. So we can run many times k-means, yes, and get the different centroids and just to pick the best one. Or we can do slightly better than the random choice. So we can choose the data point uniformly at random as the first centroid and look for all the rest that define the distance which is the closest to the centroids. So we can just do this strategy sequentially. Okay, so but again, you try and you see if it works. It works. If it don't work, okay, you go for the next method. Okay, so let's now talk about another approach to dimensionality reduction, which is called PCA, or kind of principal component analysis. So because what the centroid, or kind of what this k-means is giving us, it's give us this mapping, like that, okay, so that we can create clusters, but it's give us some ideas of the data sets, but if we want to do something else, it doesn't give us too much information. And what I wanted to discuss now, or what I want to talk about now is like, if we have a very multidimensional data, how we can reduce the complexity of the data if it's possible. So we want to reduce the complexity. So for example, you can have, entry data with hundreds of entries, and you might reduce it to the entry with the 10 entries. So if we have a correlated feature, so we want to remove them because they essentially contain the same information. And that is a little bit to the yesterday's question. sorry, what is the question is, does anyone have the notes on machine learning? Do you mean these notes or any other notes? Okay, so we can remove also less informative features or visualize the features. But the general idea is to map to from the many dimension to the smaller dimensional space. Okay, yes, somebody answered, so that the nodes are on the canvas. And how we can do it. You remember yesterday when I was describing your linear regression, and when we were doing analytics, we were representing data as the following metrics. Yeah, so kind of like where the rows are data, and now kind of like and the columns are entries. Okay, so let's now rewrite each data point. So let's take this row and write it as a column, and let's expand it in the basis in this d-dimensional space. Yes, we can always do it. Yeah. So, and from mathematical perspective, what we're doing a projections on orthogonal axes. And now the dimensionality reduction problem is looking like this. Can we take this vector of our input and project it on some other set of coordinates such that we can describe it with a smaller number of kind of axes, orthogonal axes. So kind of V1, V2, Vd, they are all orthogonal to each other. They form bases, but they form bases in the smaller dimensional space. So, and that's a question which this dimensionality reduction approach is trying to answer. And the answer is, in some cases, yes, in other cases, no. And how to decide when it's possible and what is not possible. Why do we have to move correlated features? Because they don't give you new information. If you know that, if you have a feature A and feature B, and you know that your outcome is equally improved, so that feature A and feature B are correlated, so maybe you can derive some average feature which is giving you the same information, and that will reduce your dimensionality by 1. And if you have hundreds of features and 90% of them correlated, you can reduce the space of your problem drastically. In the world of the infinite resources, it's a relevant problem, but you might also want to do it from the point of understanding. So because if you have a less features or kind of less columns in your data set, it's easier to interpret the results, or it's easier to build a simple model which can explain it. I hope it answers the question. Okay. So how we can go about looking for this new coordinate system which approximate our original data set. So, and the first approach is, and kind of the only approach about which we are going to speak in a little bit details, is called the principal component analysis. And the idea is that we want to choose the axis among the along the directions which explain the most variance in the data. So we want to build the orthogonal projections of the data onto the low dimensional space. You just imagine that, kind of like if you struggle with the word like low dimensional space, think for a second that you have a bunch of points in a 3-dimensional space, yeah, and you want to project it on plane. Yes, some sort of a plane, but in such a way so that you don't lose much information about original data, or on the line without losing of too much information. But you do it in the kind of in the multidimensional case. So, and we want to build a projection in such a way so that it maximizes the variance of the projected data. So that's, in this case, for this point, this is this axis. So because along this axis, you get the maximal distribution between the points. And it minimizes the square distances between the data points and the projections. Yes, so it's these distances. And the question is how to do that. So, and in order to do that, we need to first to say that, okay, so if we wanted to project kind of what will happen if it's a one dimension. So we want to have a f1 function such that xi is approximating f1 v1. So in that case, we need to build a projector. So in order to find the projection and make a statement what this vector v or v1 should be. Okay, so what do we want to do? We want to minimize the distance between our projection and original vector over all possible there is a hand, and that hand need to type the question in the chat. So what do we try to do? We are trying to find such a vector v such that the projection on that direction and the distance to our current vector which we are projecting is minimized. And we want to look in the whole family of the unit vectors, or in the whole family of the basis vectors, essentially. Yeah. So, and it could be shown that this operation is exactly equivalent to maximizing the variance of this product. So intuitively, if the variance of the projection is low, then V should be not very informative. Okay, so how we can find direction which maximize the variance? So what is the variance? How can we get the variance of our data? So we need to build the first, what is called the covariance matrix of all our data. And for any vector V, the variance will be a product like this. And in order to maximize this thing, we can use the fact that, the expectation value, the covariance matrix of this, because it's a product of the vector on its transpose, it's going to have real eigenvalues, and we can apply spectral decomposition theory. And so we'll have a list of eigenvalues, mathematically speaking, and it will be real numbers. And what else do we know? There will be non-negative numbers. And what can be shown that this is maximized for the eigenvector with the highest eigenvalue. And here it's assumed that all the eigenvalues are ordered in the descending order. So the E1 correspond to the largest eigenvalue. So this one will be the largest if V1 is the eigenvector which correspond to the largest eigenvalue of the covariance matrix. Okay, so that sounds not too bad, because now we have an algorithm of how to do the things. Yeah. So what do we need to do in order to construct this kind of PCI representation of principal components? And these vectors will be called principal components. So what do we need to do? First of all, in order to be able to use this covariance matrix, we need to make it to bring it to the zero mean. So we need to calculate the covariance matrix, afterwards calculate its mean and bring it to zero mean. Afterwards, we need to calculate its eigenvalues and eigenvectors. And we're starting from the first eigenvector, which correspond the first, I repeat, is correspond to the largest eigenvalue. And we're recalculating xi by using these rules. Okay? And now we just do it sequentially, and we obtain the decomposition of every our data point in the lower dimensional space, where of course xi on VD is just a standard inner product. And the typical example which you see everywhere, so if we have a kind of Gaussian style data set, but with a little bit elongated, if we apply the principal component analysis, we'll get the first principal component will be along this axis, because this axis is exactly the largest variance, or largest diversity of data, and the second component will be around here. Okay, so this is just kind of an intuitive way to understand what the principal component analysis is doing. And now, yes, kind of like how the PCI algorithm is looking like. So we have a given data. And again, we don't need to, I mean, even if we have some words written here, which I will explain to you, we don't need to know it like this, because again, scikit-learn can do it automatically for us. We just need to ask PCI, how many components do we need to have, and so on. But before we can talk about components, we need to understand what does it mean. Okay, so we have an X, which is n by d data matrix. N is the number of data vectors, yes, kind of number of input points. D is the number of features, yes, or number of columns in your data. So we need to compute mean by averaging all rows of X and subtract mean from X, so that the data is centered. Afterwards, we compute in the covariance matrix, XTX, yeah? And afterwards, what we do, we're computing eigenvectors and eigenvalues. And you can do it with multiple packages in Python. For example, this is with that NumPy, which we're loading, which is a numerical Python package, which have subclass linear algebra, and this command Ike will calculate to you eigenvalues and eigenvectors, and it will order it in descending order. So lambda 1 will be the largest one, and so on. So, and essentially, what do you have? So you have the largest eigenvalue that will give you the most variance. Now you have the second largest eigenvalue and corresponding eigenvector, and you can just recalculate corresponding representation of your original data in this new structure. And here it have the same dimension d as our original data. And now what we need, because I mean, this is, so far this is exact. But now, in order to apply dimensionality reduction, we need to apply some approximations. So, and if we now plot the eigenvalues, so we can think about, how much variance is explained. So we have a largest eigenvalue, and afterwards few more components, and afterwards, we have a whole bunch of them, but they don't explain too much, or their magnitude is too small compared to all the rest. And essentially what you're saying, instead of these 10 components, you can say that first 5 are good enough, or first 6, or first 4. It depends on how you choose the cutoff criteria. And what that will give you, if you say that first 4, you will reduce the number of your features from 10 to 4. So now instead of your data being a 10-dimensional vector, becomes a 4-dimensional vector. Very often, you get even better situations, so that kind of like these dependencies are much steeper, in the sense like, you might have a data with the hundreds of components where, first 5 will explain 99% of the data, and the rest information is essentially useless. And that means that instead of having hundreds of entry or data points with hundreds of entries, you have just the entry with 5 entries, and you can try to see how linearly separatable that data, and maybe you can even build on top of that linear model which can explain you everything. Okay, so can we use the PCA? But you see, kind of like, for example, visualization of some data sets, for example, of handwritten digits, which we'll analyze, kind of, which we'll play with in the afternoon tutorial session. But in the fact, no. And the reason why is the following. You remember, when we're building the principal components, we're essentially applying some linear operation to our, so kind of like, this is supposed to be some function of our input vector, yeah? And this function is chosen here in the simplest way, and this is a linear function. Here, this f1, f2, and so on is a linear function. And as we've seen yesterday with you, that, sometimes linear functions will work great, and sometimes linear functions are not that good. So, and if you replace this function in some smarter way by some nonlinear functions, sometimes you can get a much better results. And again, luckily for us, it's all already implemented in Python, and we can use some other tools. Yes, but so far the PCA it's a very standard pre-processing step for many supervised learning tasks. It's reduced dimensionality, eliminate multicollinearity, and could be or can be used. But you see, in this case, it's not very good for visualization. But in the example which we'll have in tutorial, it will be a little bit more useful for visualization. But what to do next? In that case, so beyond principal component analysis, which is a linear dimension reduction approach, there are some nonlinear dimension reduction approaches, and there are packages which implement them. One is called isomap and another called TSNE. And TSNE, for example, on the digits data sets, gives you the perfect clusters. And you can see that you can reduce the dimension of your data set without kind of neural networks to achieve a very good precision using some nonlinear transformation, because each blob here corresponds to the one of the handwritten digits. For example, this could be the class 0, this will be class 1, this will be all the class 7, and so on. Okay, but the problem with the nonlinear, so that they are hardly to optimize, and because nonlinear there is also less guaranteed, and so not so easy to interpret, and so on and so forth. But just keep in mind, so if you need to do for your data set, if you need to do some dimensionality reduction, you can always try PCA as the first line of attack. But if it doesn't work and you're still convinced, for example, your data is not that large so that you need to go for the full-blown neural networks, you can apply some nonlinear dimensionality reduction approaches to obtain some nice results. Okay, so that will be it about everything before the neural nets. And I assume that we're supposed to have a break in 5 minutes. So let's have a questions if there are any, and let's have a break. And after the break, we'll do the neural networks.
Okay, Prof. Thank you. I'm not sure if you answered Rahul. I had a question. Why do we move correlated features? I'm not sure if you answered.
Yeah, I think I answered that, just because, if we have a correlated features, they contain the same information. So we don't, if you have a 5 features, maybe you don't care. But if you have a 10,000 features, if you can reduce that number to, to 5, that is much better.
Here I see Eunice is typing. So Adeshina, please ask your question on Slack.
Guys, and it's time to learn that you ask all the questions on the Slack. It's already the 2nd week. You can, the question is like, can you apply dimensionality reduction to all kind of data sets? In the moment when you can transfer all your input values of your data set into the numerical values, yes. So the housing CSV, which we used from yesterday, yes, except, we still need to throw away the addresses, because we just need to, again, it's like, we throw away the addresses, we get only numerical columns, and in that case, we can apply the dimensionality reduction. Hi, Prof. I've seen people use PCA for the gene expression data. If we have a data set of 100,000 genes with expression data for the disease, what are just single numbers, positive of negative? Will these maps be useful to cluster important genes, whether the person has disease or not? Yes, I assume so. No, because maybe, you know, PCA might be not so important, but, you know, the idea is that, you know, PCA and similar approaches will give you kind of like a non-linear like TSNE, which just can give you the clusters and you can see what are these clusters about. The only thing is what one need to be careful is like when you're talking about the data sets of genes, how you define the distances. So, and how kind of like it's not just how you interpret the particular, you know, genetic characters. So, but this is up to the, you know, okay, so I'm not sure what does it mean, gene A plus 1.6, gene B minus 10.4, but you know, you just need to try, and if it's useful, you use it, and if it's not useful, you don't use it. And more so, I didn't catch well how to know the optimum dimensions number. The optimum dimensions number for PCA is very simple. You know, you need to see, you know, how much of variance is explained, or, you know, what is the good proxy, what is the size of the eigenvalues for each component. And the optimum dimensions number, of course, you want, I mean, you know, if you want to visualize, you want 2 or 3. But, you know, it could be that the 2 or 3 do not explain enough of the variance. But you can try and see, does it give you enough information or not? But you just try and see. You take 2 first component and plot all your data and see, do you see some clustering or do you see something which is useful? And if it's not enough, you add 3rd component, 4th component. But, you know, here again, if we say that 5% is a cutoff, we can reduce from 10 to 4 components. But this is strongly depends on the data. You know, you just need to see, you know, how quickly the eigenvalues are going down. Because I assume that you might have a situation so that, you know, there are many components which contain a lot of information. And unfortunately, in that case, at least, you know, these linear methods might be not that efficient, but you can try nonlinear methods. And again, when you do this TSNE, you need to tell, you know, how many axes you need to have. You know, do you want to have a 2 axis, 3 axis? You try and see. Optimum depends on the data. Yes, it's like exactly as the elbow curve for the number of clusters. You see kind of when the increase in the number of clusters is giving you good results or not. You know, when you increase the parameters and that doesn't give you any new information, you stop increasing the parameters. Okay.
Okay. Thank you for the questions. We will take a break now, and we will be back at 11:15.
Wonderful.